Hello, today we'll be looking at RL series circuits. When an inductor is connected in an AC circuit, its opposition to the flow of current is determined by its inductive reactance. There's a direct proportional relationship between the frequency of the supply and this reactance. The inductive reactance is therefore given as XL being equal to 2 pi FL, where F is the frequency in hertz of the supply, and L the inductance of the inductor measured in henries. Now, if we consider the circuit shown, at the point I close the switch, the voltage across the inductor is equal and opposite to that of the supply according to Lenz. This results in the circuit current being initially zero. The general impact is that the voltage across the inductor is leading the current through the inductor. In other words, the voltage across the inductor is seen before we start experiencing a current going through the inductor. At the same time, however, the voltage across the resistor, which follows the current, will also be zero. Okay, so the current and the voltage across the resistor would be behaving in a similar fashion. We can represent this graphically. So having that graphical representation, here's my circuit current. And it's in phase with the voltage across the resistor, as we just pointed out. So the voltage across the resistor is in phase along the same line. The circuit current, again, reference to Lenz's law, lags the voltage across the inductor by 90 degrees. Or in other words, we're seeing it after the voltage. So if the current lags, then it means that the voltage leads. So that's VL, and we have our 90-degree angle. Now, at all times, the supply voltage, because we have a closed loop in our circuit, at all times, the supply voltage will be the sum, albeit in this instance, a vector sum, will be the sum of the voltage across the inductor plus the voltage across the resistor. And in finding that vector sum, we are able to find the supply voltage. So by Pythagoras' theorem, considering what we have here, by Pythagoras' theorem, it means that Vs squared is equal to VR squared plus VL squared. And if we refer to Ohm's law, where we know that by Ohm's law, V is equal to the, the current rather, is equal to V over R, we can apply that to the inductor, because if we know the inductive reactance, then the current through the inductor would also be V over XL. So we make those substitutions, these two substitutions, into our equation. Making the substitutions, this would be Vs, this is VR, and that would be VL. And we make the substitutions, but of course, because we're dealing with a series circuit, all the currents are equal. So we simplify the expression for Z, and we're introducing a new term, Z, and Z represents the impedance of the circuit, and it is also measured in ohms. Now, because we're looking at vector sums, it is important that we are able to determine what is the phase relationship between your current and your voltage. And we're using the reactance, resistance, and impedance to show that. And so this angle we refer to as the phase angle. The phase angle phi is the inverse tan. If we complete this, we would have a right angle triangle, is the inverse tan of XL to R. Okay? This would be equal to XL. And so theta, or phi rather, is equal to the inverse tan of XL over R. Now that I have all this information, let us see how we apply it to circuit analysis. The circuit shows a 19.1 millihenry inductor connected in series with an 8 ohm resistor, and the combination is then connected across a 30 volt 50 hertz supply. We want to determine the current flowing through the circuit. Now, the first thing we need to determine, or what we need to find, is that, sorry about that. So we need to determine the current, which is given by V over Z. But of course, Z is equal to the square root of R squared plus XL squared. And XL is equal to 2 pi FL, which for this example, it's 2 pi times 50 times 19.1 times 10 to the minus 3. And this is equal to 6 ohms. So the impedance Z is equal to the square root of R of 8 squared, that's R, plus 6 squared, which is equal to the square root of 100, which gives us 10. So the impedance is 10 ohms. But we also need to determine our phase angle. Phi is given by the inverse tangent of XL over R. So that's the inverse tan of 6 over 8, inverse tan of 0.75, and we calculate that, and we get 36.86 degrees. So our current, I, is equal to 30 over 10, so the magnitude of our current, which gives us 3 amperes. However, we must indicate the phase angle. And we know, as we said earlier, that for the inductor, we see a voltage before we see a current. So the current would be lagging the voltage. So I is equal to 3 amperes at 36.86 degrees lagging. Written another way, I is equal to 3 at minus 36.86 degrees amperes. We thank you for your attention.